Good day. Welcome to this edition of the IPC Thought Leaders Program. I'm your host today, Roger Franz. Our topic is the future of carbon electronics. C is for carbon. What about the future of carbon electronics? Why is carbon of interest for future electronics? What kind of carbon will it be? Where will new applications using carbon be found? And how can carbon electronics be successful and sustainable? First of all, why carbon? I personally noted the following items in a prior IPC Thought Leaders program called Electronic Materials Vectors to Circles. More than half the naturally occurring elements are used to make today's electronics. This complex demand on our material supply chain could be simplified by using carbon. Reliance on toxic or critical elements could be reduced. Carbon is an abundant starting material and could be recovered or recycled. And of course, the full life cycle considerations should be made part of carbon R&D. Now, carbon is not new to electronics. You see a familiar axial resistor here. And think about the element carbon. It's not just carbon dioxide gas, which is implicated in climate change. It's the solid element, carbon itself. Carbon is a fairly weak conductor, not technically a semiconductor, as we usually think of them, but it's a good enough conductor and a poor enough conductor at the same time it can make a very good resistor. When combined with other elements to make polymers, for example, it becomes a very good insulator, like the resistor body shown here, component packages, substrates, wire insulation, and so forth. Carbon compounds, called organic by definition, are in all kinds of products and, of course, life itself. But it was the recently discovered forms of carbon that sparked new interest. Enter nanomaterials. It was in 1996 that the Nobel Prize in Chemistry was awarded to these gentlemen, these scientists, for their work on what's called fullerenes, as you see pictured here. These are made entirely of carbon linked together in a three-dimensional structure, kind of like a ball. They are very small. Nanometers are their range, 1/1,000,000th of a meter, very small indeed. That's the definition of a nanomaterial in that size range. Could be almost anything, not just carbon, but here we limit ourselves to carbon nanomaterials. Now, fullerenes have been around for a while. It was the visionary R. Buckminster Fuller who designed geodesic dome structures that look similar to the carbon-60 molecule. Buckminster fullerenes became known as fullerenes or simply buckyballs. These molecules had been identified in outer space, and the name fullerenes existed for some time before being synthesized and characterized by the Nobel team and other scientists here on Earth. Here we see a picture of the main types of carbon, or the allotropes. These familiar forms, for example, diamond as in a ring, graphite like pencil lead, which of course is not the element lead at all, and regular amorphous carbon, which means it really has no structure, are very familiar to all of us, but those are not nanomaterials. These are examples of nanomaterials. On the lower left, buckyballs are fullerenes we have already mentioned. On the lower right, nanotubes, usually called CNTs, carbon nanotubes, or graphene up in the middle, a flat structured layer, are all nanomaterials, and in fact carbon nanomaterials. Now, what about application? What can we do with this neat stuff? Well, it didn't take long for researchers to realize that a carbon nanotube was a great candidate for making all kinds of electronic parts here. You begin to see the terminology carbon-based electronics used here. Here's an early citation making carbon nanotube field effect transistors. In the middle, we have examples, all kinds of other electronic devices made, displays, PV cells, sensors, fuel cells, batteries, not necessarily circuit board based, but still electronic in nature. And of course, carbon nanotubes, as being a great conductor, can make good wires. More conductive than silver, stronger than stainless steel, carbon nanotubes are one of the many ways we're innovating material science. One of the scientists at the company where I work. You can easily telegraph the growth of new buzzwords. For example, just do a Google science search and you can count the number of hits you get across the literature, including patents and citations. Some decades ago, there wasn't much in the terms of carbon nanotubes or transistors being cited, but now you see in the late decade, it's ballooned into hundreds of thousands of citations per year. So enter yet another carbon nanomaterial called graphene. Again, another Nobel Prize. I need to give credit to the true thought leaders here. It's so thin that they exhibit quantum mechanical properties, pretty cool. Graphene sheets conduct electricity as well as copper, which is great. They conduct heat better than any other known material, good for getting rid of thermal problems in your devices, and are so dense, and if you want to, they can block helium atoms. I guess they'd make good expensive balloons. So graphene sheets are one carbon atom thick and commonly classified as two-dimensional materials. In fact, you'll see the buzzword two-dimensional devices in the literature as well. I really need to mention the International Roadmap for Devices and Systems. It's all about future devices and the systems they will enable. Again, a lot of thought leadership is available in these monographs. To quote one of them from a couple of years ago, among emerging logic devices, carbon nanomaterial device, mainly carbon nanotube, field effect transistor, tunnel FET, and nanowire FET were ranked as one of the most promising emerging logic devices. And a few years later, another even more promising carbon nanomaterial is now emerging. Graphene can offer possibilities for employing novel switching mechanisms for future electronics. The 2020 IRDS report lists these different trends. First of all, Moore's law is reaching its limits. They talk about more and more, that is, shrinking existing geometry device even more, using variations like 3D stacking. Beyond CMOS, which includes all kinds of new novel ideas, emerging architectures, emerging devices and processes, and emerging new materials. Within the 121 odd pages of this monograph, the word graphene appears over 150 times. So you see, it's of great interest in the research literature for electronics. So it didn't take long for researchers to go from CMOS to GFET. G is for graphene, of course, and here you see an example of such a device. To quote these authors, complying with Moore's law to increase transistor density of an integrated circuit, new alternate materials for fabrication have been tried instead of silicon due to limitations in reducing transistor dimensions. Graphene, one such material, proves to be a suitable alternate for silicon. GFET is becoming the most suitable choice for high-speed analog VLSI RF and biosensor circuits. So here you see a small channel, and of course, key there is the graphene channel. It didn't take long to go from transistors to ICs, and the same is true in the modern world. The first graphene integrated circuit was announced just over a decade ago, and although there's still a lot of work to be done to improve the device and circuit performance, it represents an important step toward useful circuits. It will be several years before graphene devices are ready to displace conventional silicon circuits, which are expected to start hitting their limits later this decade. Well, there's a prediction. Of course, Moore's law continues to be extended, but we need to find the next generation. Graphene comes to the rescue of molecular electronics, quoted just a few years ago. I believe that is really the case. It's going to be a great savior to continue the advent of electronic device development. But the naysayers say graphene has no native band gap. Well, just to define terms here, semiconductors like silicon and germanium have a band gap, which is an energy level between, or a gap between the electrons used for chemical bonding and those available to move around as conductors. Typically, they are doped with small amounts of donors or acceptors, your N or P type, to fine-tune the properties. As often happens with the new discovery, challenges are taking head on. So what if there's no band gap? We'll make one. You see a couple of companies announcing graphene with a band gap and good electron mobility here. No doping or nanostructuring is required. A new bottom-up approach to grow graphene makes a perfect band gap. So where there's a will, there's a way. And I need to highlight that graphene is not going to replace carbon in our environment. Graphene will be used in small but critical amounts. Other materials will still be needed, but if we have novel forms of carbon, we can use it instead of so many other kinds of novel materials from the supply chain. It's not about replacing them all with carbon, but certainly selected a few of those. Material options for graphene in one report still include other materials, but you see that conductive graphene is part of it, and multi-layer graphene is a critical part of these other new devices just being developed. Carbon nanotube devices can be put into conventional packages today and assembled using conventional circuit board assembly processes. But I do predict, in fact, everybody who studies this literature does predict, in the coming years, carbon nanomaterials will enable printed and flexible electronics, which will require manufacturing processes other than circuit board assembly. So what would those be? New applications using nanocarbon would consist of not only carbon nanotubes, multi-wall nanotubes, but of course graphene, and their efficient physical, chemical, and electrical properties, such as high conductivity, efficient thermal and electrochemical stability, and high specific surface area, enable them to fulfill the requirements of modern electronic industries. Energy storage, batteries, and supercapacitors. Self-powered automatic sensing devices like biosensors, gas sensors, pressure sensors. Molecular electronics and molecular devices themselves, and finally multifunctional wearable electronic devices and systems. It's that last point of wearable and flexible electronics I'd like to spend just another minute on. Flexible electronics is a new buzzword enabled by largely graphene. Printed electronics technology is enabling both conductive materials such as copper and silver, as well as emerging materials like graphene and organic semiconductors to be printed directly onto flexible circuits on a wide variety of substrates. It is now already possible to print more advanced components such as capacitors, transistors, antennae, and batteries, all on the same flexible substrate as traditional electronics. This will enable future electronics that are thin, lightweight, flexible, stretchable, and wearable. These will become integrated with ourselves as humans more than ever. And again, the buzzword is growing. If you again do a Google Scholar search on flexible carbon-based electronics, you see a lot of hits here in the last decade. It is definitely growing and catching on. You even see textbooks now called flexible carbon-based electronics. You see several volumes of that already in print. I need to add to the end of this story to close the loop on life cycle about sustainable success. Graphene is not based on rare or critical elements. Luckily enough, carbon is all around us. In fact, there's some reports now that graphene can be made just by flashing, literally sparking trash, which is full of carbon. So you take a joule heat, that is, you apply a current that heats up thing like a wire, you zap it essentially at high temperature for a short period of time, and it can produce high quality graphene right there. Requires no furnace, solvents, reactive gases, purification steps. It generates very little excess heat. Nearly all of the energy channeled into its target. Pretty cool stuff. So I followed Dr. James Tour, who's quite a guy in his own right. He's done a lot of research I've followed for various types of technology. He's a big champion of graphene. There's a video he's presented here. I don't have time to show it all, but it explains in very comprehensive and scientific fashion the case for graphene research here in this country. And honestly, it's all about a bit of good old carbon entering a very big new life. Now, we're not alone. Obviously, at IPC, I'm a watcher here. These organizations are actually dedicated to graphene. You see in the EU, the Graphene Flagship. It's part of the European Union's biggest scientific research initiative, the budget of €1 billion. The project represents a new form of joint coordinated research initiative on an unprecedented scale, Graphene Flagship. And not to be outdone, here in the U.S., the Graphene Council, org, was founded in 2013 with a mission to serve the global community of graphene professionals. Today, the Graphene Council is the largest community in the world for graphene researchers, academics, producers, developers, investors, nanotechnologists, regulatory agencies, research institutes, material science specialists, and even the general public, guys like me. They reach more than 50,000 people with an interest in this amazing material. And within our own U.S. government, as just a third example, nano.gov is working together toward the shared vision of a future in which the ability to understand and control matter at the nanoscale level leads to a revolution in technology and industry that benefits society. Yeah, I really believe there is promise here. Now, like any technology, there need to be standards to kind of commonize how things work, level the playing ground, give us common terminology, tell us how to measure thing, characterize thing, Especially with the new technology, we have to worry about environmental health and safety effects here. You see some standards there. And finally, to educate the public on what nanotechnology is all about, put it all together, you see quite a number of standards here who are enabling graphene development. Regulation-wise, I'm a regulation guy by background. Luckily, there's no hard bans or anything on this new material yet, but like any technology, we must be cautious, in fact, very cautious at the early ages before everything gets out and now we have to control and pull it back. The US EPA, for example, is working collaboratively with stakeholders both domestically and internationally to address nanoscale materials and research needs and develop international standards for nanotechnology. In the EU, nanomaterials are covered by the same rigorous regulatory framework that ensures the safe use of chemicals and mixtures like the REACH and CLP regulations. This means that hazardous properties of nanomaterials or substances have to be assessed and their safe use needs to be assured. Yes, indeed. So carbon nanomaterial development must be proactive now to understand and address environmental health, safety, and life cycle aspects to ensure reactive regulations do not enter into force later on. Now is the time to get it right. As a person who reports a lot of legacy substances in our products, things like heavy metals, this is definitely the time to get it right with nanomaterials. So the promise is there. Versatile and abundant carbon is enabling breakthroughs in nanoelectronics, and you really haven't seen anything yet. It's just beginning. Flexible electronics may create new products made with printing, a novel new manufacturing paradigm. And industry, academia, and governments should partner to make nanocarbon electronics truly sustainable and safe from the start. That's it for my little carbon spiel. Thank you for listening. Appreciate your time. Thank you.